Hello, everyone.
Hello.
How are you doing, Tyler?
I'm good.
Great. How is your lab? We finished the lab and homework part B. Have you done those?
No, I did not finish the lab.
Okay, please watch for the deadlines. Hello, Paul.
Hello.
How are you doing tonight?
I'm doing pretty well.
Oh, very good. Are you ready now?
Yeah, let's do it.
Okay, I'll share the screen. Can you see the PowerPoint?
Loading.
Okay. I don't know why it is taking a long time. Now it is not starting. Any suggestion?
Run as an administrator.
You can see it. I'm trying to start my PowerPoint. It is not starting.
It,
Like run as an administrator. Maybe that will work.
I'll reboot my system. So
I don't-
please
you just hit Control-Shift-Escape.
Control Shift Escape. Yes, to go.
to go into your task manager and then end
Okay.
the PowerPoint process. If it's running, click the more details.
It is not here. It is not starting as you can see it.
Yeah, click the more details just to make sure on the bottom left of that window. Yeah.
More details.
Yep. And,
No PowerPoint.
okay, well, I don't think rebooting is going to fix it. Just try double clicking it again.
Oh, here we are. Great. Thank you.
Yeah.
In the last meetings, we finished with generate, debounce. Now we're going to speak about clock domains. Clock domains we may have a system like this one. You can see the processor is working at a speed 528 megahertz. And it is speaking with the memory. Memory is not that fast. It works at a different clock, 132 megahertz. And I might be working with other peripherals, and each one may have different clocks. So each part will have a clock domain. And I need to cross the clock domain of the processor to the memory. So this is called CDC, clock domain crossing. Clock domain crossing, I need a software that would enable the memory to send and receive data from the processor that's working at higher frequency or lower frequency. So I need to communicate between multiple systems that may not be working at the same clock using CDC, clock domain crossings. If clock domain crossing is not well designed, I may get into a metastability. Metastability means that upon the rising edge, I have data that has thus just changed to 1, from 0 to 1. That is upon the rising edge of the clock. Okay, but we know for any response to happen, I need to be before the rising edge available, the data should be available, the 1 should be there before the rising edge by what's called setup time. Not only that, I need to remain high. 1, the data should be 1, even after I reach the rising edge of my clock by a hold time. If the setup time or the hold time are not very well observed, I may not get the correct data. I may get myself into what is called metastability. Metastability means my signal is changing, yes, but it didn't reach 1 and it is not 0. It is something in between, trying to travel to 1, but it hasn't reached 1 when we are at the rising edge. So this is called metastability. Metastability may give you an error message or error data. Those are metastability examples. I have, this is my clock 1, and this is my D input for this D flip-flop, this memory bit, and I have here Q. And my next state of state machine, it is working at a clock 2. So I have here a CDC. Now I have next state, it is fed back here. So I may not be ready for Q when this is fed back. So this may cause metastability. You can see state register is working at 1 clock, clock 2, and here I have a clock 1. This is another example. I have a RAM and I have data. This is working at a clock and this is another clock. So I may get metastability. 2 D flip-flop. This Q is setting the second one. But here again, I have different clocks. This data is transferred from one system to another system, again at different clock. So this will cause metastability. For this system, we have what? we have the first data coming here and it's coming out at A clock, and it is feeding another system. This system, A data is coming here, and it will be B data 1. This B data 1, it is working at B clock. Now let's trace it very slowly. This is my A clock, and this is my B clock. This is my A data here. This is my A data. This A data, it is working at this A clock, and it is working fine. I am going high with the rising edge, and I am going low with the next rising edge. This is the data here that is feeding system 2. Now let's go and see system 2. How will it behave? I have this A data available here, and it should be transferred to B data upon the rising edge of clock B clock. This is my B clock rising, and A data is 0. So it would remain 0. The second rising edge, it is rising in here, while A data is on transit from high to low, And this is happening exactly at the same time of the rising edge. This signal, to be correct, it should remain high until I end up with my hold time. Yes, it is there before the setup time. Very good, but it should be here for at least the whole time. But it went fast from 1 to 0. What will be the output here? The output here will be this thing. Meta-stable data. This is a meta-stable data. What about the second B clock? The second B clock, I have here 0, a very stable 0. So I go to 0. I am not sure if I have reached 1 or 0 in this state, in the meta-stable state. Clear, Brandon?
Yes, yeah, it is.
Okay, thank you very much. Another example is this one. I have here combinational logic. I have this D, I have this Q, and this is clock A, and feeding this system with clock B. Here I'm trying to mitigate the problem of meta stability. How could I do that? By having 2 cascaded flip-flops. Let's see how those 2 cascaded flip-flops will resolve the issue. This is clock A, and this is my data. Clock A is here, and my data is changing here. Because of that, I have here this D over here. It is in a meta-stable state. Meta-stable state means it needs to go high. And it started going high. But with the end of the rising time, it didn't reach the full height. It is something in between high and zero. And this is operating at clock B. And with this second clock B, here I reached my high. Clock B came while D in is very stable. And I have here DS. Very good signal, high. This DS is feeding the second flip-flop with appropriate setup time and hold time. So my D out is here. You can see the D out here. It went through 2 B clocks to be stable. But this is the correct output that matches D in. But I need an extra D flip-flop to make sure that I reach my stable state. This is repeated in here. A data, and I have here A data. It is similar to this one, but here I modified the circuit by having 2 cascaded D flip-flops. I have the first one metastable, but upon the second B clock, BQ2 should reach a very stable state and be reflecting A data, but it's on its own clock. So one solution for metastability is having 2 D flip-flops cascaded. We call it synchronizing. Let's see another example. This synchronizing system may fail if you have a very fast signal. We are trying to map it into a slow clock signal. Very fast clock signal. We are trying to map it into a very slow signal. Let's see this. Here is my A clock, and this is my B clock. My data is according to the A clock. So it went up here, and with the following rising edge, it went down. For the B clock, what will it see? With this rising edge, I see 0, a very nice 0. So it is 0. Here is 0, I will get here 0, I will get here 0. Now, let's go to the second B clock. My A data was high, but when the very slow clock came in, it was low. So it didn't see the high at all. So it remained 0, and BQ2 remained 0. So I missed this data. For having something like this that is mapping very fast signal into a slow clock domain, one solution is called open loop solution. I should have A data extended to 3 clock cycles. Or I can say to 2 clock cycles of the slow one. This is my slow one, I extend this one. In this case, this is my B clock, and I have my A data. Even if it didn't catch it well, it would catch it as a metastable. And upon the second B clock, it will be a very good signal. So I will get here BQ1 very well, and BQ2 will be even better. So by extending the pulse, lengthening the pulse, I can have this. I need the extension of the pulse to be at least 1.5 of B clock, at least 1.5 of B clock. If it is too big, 2 of B clock, that would be great. Switch debouncer that we had in our previous lectures still can help in this regard. I am comparing output of Q1 and Q2. And I am waiting for certain time using the XOR to keep the counter clear, 0. When I have them equal, I will have, if I have those two identical, I will have here 0. So the S clear is not asserted. So I can start my counting. After certain amount, after I reach the terminal count, I am having enable that will give me the output. I believe we did that before. The previous one was what is called open loop. It is fast and no acknowledgement to signals are required. But sometimes a designer may feel this is the optimum and it will work for any system. No, it will not. It is designed for those certain frequencies. If we have a change in the frequency, this will not work. I need to rechange everything. I need to rechange the extension of the pulse. We said it is 1.5 of B clock. So I need to extend this. Here, I need to change the terminal count of the N bit counter. So it will not work for everything, but the disadvantage that a designer may feel or may think it is the final and it doesn't, it is very consistent for any system. No, it is very well designed for one system only. If there is any system change, everything would change. Now we go to a closed loop scheme. In this closed loop scheme, we are starting with what is called handshaking. Handshaking scheme. In this one, we are going through several steps. First of all, what do we have in here? I have a system that is working with a clock. All of this system on the left it is working at A clock. And I have here another system that is working at B clock. Okay, those are my two systems. If we have at the very beginning, this is A clock, and this is my B clock. All of those are for system A, and those are for system B that's working with the B clock. Now let's track the system and see what is going to happen. First of all, I have this A data. It is coming in here. And upon the rising edge, I have A data 1 is going high. To follow A data. A data is high, and I have here A clock. So A data 1 is high. Hello, Daniel.
Hello.
Would you please track with me what is going on?
I'll do the best I can.
Okay. Here, if we are to look at this A data 1.
Okay.
Okay. And I have BQ1 and I have BQ2. I have here A data 1, this one. Is this correct? BQ1?
So BQ1.
I have A data 1 in this format.
Okay, so when A data 1 is high,
It is
and then,
high, and I have here a rising edge. What will happen?
Then the BQ1 data will go high.
Okay. Now, BQ1 is here. What about BQ2?
So at the next rising edge, BQ2 will go high.
Now I have this BQ2 here is high, and it is being fed here back to AQ1. Please note, AQ1 is working at
The other
A clock.
Yeah. So when A clock goes high or rising edge,
yes.
Yeah, then AQ1 data will go high.
That is AQ1, that is right in here. Now, what about AQ2?
So then when A clock has another rising edge, and AQ1 data is high, AQ data will go high.
Now, when I have this AQ high, that means I acknowledge it, that the system B has received the data. So if the data change, no problem. Here data is changing according to A clock. So A data 1 is going low, and the cycle repeats for going low.
Okay. So it
You can
triggers
see here,
off of two separate clocks.
yes, I received at the end my data. It is very correct, but I have to go through all of those stages, and that is quite time consuming. But the integrity of data is well observed. This is one example of how we may make handshaking or synchronizer. Those are the advantages and disadvantage. Advantage, we are having a safe data, and disadvantage, it takes a long time and many components to achieve. If I have more than one data, a stream of data is being transferred, and I need to synchronize it. Now we have many techniques for synchronizing multiple signals, not just one signal, multiple signals being transferred across different clock domains. With these multiple signals being transferred through different clock domains, we have a system like this one. What do we have in here? This is multi-bit CDC. This is the system with clock A, and this is the system of clock B. Here I have my data. This is my control signal. This is my control signal here. This control signal is working with clock A. And I have here, this is my synchronization, 2D flip-flops. I have this coming out, and on the B clock, I have this high, B clock, this will go high, and B2 will assert it to be high. So I have next my data is here. This is a multiplexer. What does it do? If I have high, I will take this as my input and send it out. If I have here low, I will take the input 0. What is the input 0? My input 0 is the output Q. So it would remain in the same stage. Remain same stage, no change. Unless I have here high, I will get a new data. So I will get new data when here is high. So I am getting my control signal that is happening at clock A. At this point, the control signal passes through the flip-flops, and it is available here, high. Now I am taking my data upon this second flip-flop output high. I am selecting to go to the new data that is available in here. After I get this, it will go low. Low means remain as is, no change, no change. When this input is low, I keep on the same data until I reach another control signal to get a new data. Then I will pass the new data availability through 2 D-flops that are working on clock B domain, And I have here high in the mux, so get the new data out. Hello, Louis? Hello, Louis?
Oh, sorry, I was off for a sec.
Okay. Is this clear? Do you want me to repeat it?
Yeah, can you repeat it for me?
Do you want me to repeat this?
Yeah, sorry, I was off
Okay.
my computer.
This is the control signal that tells my system that this data is ready, so grab it to the output. So this my control signal here.
Okay.
When it comes, it is gonna follow the A clock. This is my A clock. Upon the rising edge, I have the request for new data. And this is happening and being transferred to the output right in here. Next, I have two D flip-flops in cascade, but those are working on another B clock. This is the B clock. I have here this output high, but I didn't catch it. But here, I managed to catch it, and it went high. And this is fed to the next one. That is happening in here. When the next one received the high, it opened this gate because this mux has two inputs, input 0 and input 1. If I have here 1 coming from this B2, if I have 1, it will open the stream for this Q to go to the output. And it did go to the output, as you can see the change in output. Here, I have my A data went to 0. So my control went to 0, and here will go to 0, and here will go to 0. When I have 0 here, the mux will do what? Will take the output and feed it back to the input. So I would remain the same. Here is remaining the same. Clear, Louis?
Yes, thank you.
Thank you. Are you ready, Louis, for this big one?
Yes.
Okay. We have here a system that is similar to our homework A. In this system that is similar to homework A, I have two state machines, state machine A and state machine B, or sender finite state machine, receiver finite state machine. What I need to do is this data that's available here, I want to transfer it to the second system. And the two systems are not working at the same clock. This is clock A domain, and this is clock B domain. How we do that? First of all, I have here the data. I am enabling the data to be available on this bus. System B didn't grab the data yet. But I have here the data. It is enabled. Okay. Now, this state machine is sending a request to system B to grab the data. And this request must go through two D flip-flops to make sure that everything is stable. 2 D flip-flops. Here, the receiver end. It received here a request on its own clock that there is data available for you. What it will do, it will enable its channel, receiving channel, to open and get the data. Meanwhile, it will send back to system A, to the sender, acknowledgement saying, I received the data and the data is very good, thank you. And to send back this message, I have to go through a synchronization system that is 2 D flip-flops in cascade. I received the acknowledgement. Now, this system may enable new data to be available and send another request, and this request will be synchronized. When it is received, it will enable the grabbing of this data and send back acknowledgement. And that would keep on going on and on forever. Hello, Kobe.
Hello.
Would you please go with me through this timing chart to see if it represents whatever we have been saying?
Yeah.
First of all, I have A enabled. Can you see it?
Yes.
And it is here. And it is working at A clock. It went up for 1 clock cycle. And since it went for 1 clock cycle, I have my data here. Can you see how it changed?
Yes.
Now this data is available on this bus. Now, please track with me what is happening right in here. This is my request. When the data changed and it was available, I sent my request. Can you see the request?
Yeah.
Going high. Going where? It is going to the B system. Going to B1. Correct?
Mm-hmm.
So B1 will respond according to the B clock. Correct?
Yeah.
The request, but it will go to B1 upon its own clock, clock B. So here it reaches the rising edge of clock B, so I have this B1. And B1 is fed to B2. And B2 would require another clock cycle on the B. Now I have this queue. This queue, it is saying there is some data available for you. Please enable B. Can you see? When it came, it enabled B automatically for 1 clock cycle of B. And when we have it here, it is enabled. We grabbed this data Can you see the data change?
Oh, yeah.
Then I am sending back the acknowledgement. This is my acknowledgement. Acknowledgement, this one, it is following clock A. I'm going through A1 and A2. So this is A1 followed by A2 from my acknowledgement. Now I acknowledge that I have data and I am ready to enable or to start a new cycle. Clear, or do you want me to repeat it? I have no problem with repeating it several times.
That makes sense.
Okay. Hello, Bart? Bart,
Yes.
clear, or do you want me to repeat it?
Not 100% clear, but
Okay, okay. We can repeat it. We have very long night, don't worry. First of all, this is my enable. When it goes high for 1 clock cycle, it permits the data to be available on the bus. And if I have the data available on this bus, I next send a request to the receiving end. I will have data, I have data ready for you. Since the request is coming from clock A to a clock B system, I go through 2 cascaded D flip-flops to make sure it is stable. Here is the receiving end. It received a request. When it received this request after 2 B clock cycle, it enabled its data grabber. The data grabber got the data that was available on the bus, and it is very polite, so it should say thank you. So it sent back an acknowledgement to system A. And this acknowledgement should pass through 2 cascaded D flip-flops to be synchronized to the A data clock. Here I have it, the acknowledgement received. When I receive the acknowledgement, I may now enable a new batch of data to be sent to the data bus, and I send a request. Request is received, data grabber is enabled, acknowledgement is sent back. Are you ready to go with me through this timing chart?
yeah.
We said the first thing is I have an enable signal. This is my enable signal. It is going out for 1 clock cycle of A, correct?
Yes.
And this is my data. It was here available on the data bus at this stage. Okay,
Okay.
this is my data now. When it was enabled, it has changed. I permit the change, whatever the stream is. When I have the enable means get the data ready. So the data is now ready. Shall I continue?
Yep, I'm following you.
Okay. And when the data is available, that is at this point, I am sending a request. This is my request. This is my request is going high, and This request is passing by two B flip-flops, B1, B1, B2, two D flops, B1 and B2. Now we have, this is my request. Here, it will come out here, out of B1. But it will come out of B1 upon the rising edge of clock B. Can you see the rising edge of clock B?
Yes, I can.
I have here B1 going high. And after one more clock cycles, B2 will go high. Now, when B2 goes high, it immediately enables B. This B, it is my data grabber. Now it is enabled for one B clock cycle. This is the one. And you can see the data here is changing. I enabled the change of data, so I grabbed this data. At the same time, I am sending back acknowledgement because I have the data now. So I'm sending back acknowledgement. The acknowledgement will go to A1 and A2. A1 and A2, do they follow clock A or B?
It should follow clock B.
A, yes. So this is the acknowledgement. It is going to A1 according to its clock, followed by A2 according to the A clock also. After receiving the acknowledgement, I am ready to enable a new batch of data. Clear?
Yes, and this is handshake synchronizer.
Yes,
What's a
handshake.
hand-
Yes,
what's a
it's
handshake
for, this is
synchronizer?
if we have stream of data going in, multi-bit CDC.
Okay, so it's just like kind of having two systems communicating to each other.
Yes, excellent, that's it. Hello, Joe.
Hi, how's it going?
Do you want to repeat it? Is it clear enough for you?
No, I got it. Sounds good.
Okay. Hello, Cody.
Yes, sir.
Clear enough?
Yeah, I think I get it.
Are you ready for the big show?
Sure, why not?
Okay. This is our homework 5A. As I said, it is very similar to what we have just seen. State machine 1. This will be sending the data. So it will enable the data, as we said. Here it is, the data source is a counter. When I enable the counter, it will count. So the data here will be what the next count. Whenever I have enabled, I am getting here an increment of the counter. So I have a new data. So I am starting by enabling the counter for one clock cycle of A. And here I have increment of the counter. And I am sending here a request. that goes through a synchronizer. Synchronizer is two cascaded D flip-flops. It is received by state machine 2. What it does, it enables the register to read, take the data, put it on the output. Meanwhile, it is sending back acknowledgement through a synchronizer to the flip-flops working at clock A to state machine 1. When state machine 1 receives this acknowledgement, it goes back to the counter with an enabled signal to increment and have a new data available and send a request. I am gonna give you all 10-15 minutes to think very, very slowly about this one and read what we have. Mainly, I have three inputs: A clock, B clock, and reset. Whenever I have reset, I can reset everything to 0. My output is this one single output of the whole system. I have one output. What I want from you after reading, you are going to see it is the same as we did. And this timing diagram will be similar to the one we saw before. And it will explain to you how many states do we have in state machine 1 and state machine 2. How do we move from one state to the other? So after you read, I'll give you, as I said, make it 20 minutes. After 20 minutes, I'm gonna see with you what is the state diagrams of state machine 1 and the state diagrams of state machine 2. If we have correct state diagrams, we can translate it into VHDL code, and we know how to do that. Okay? I'll stop sharing and I will let you work on this problem. Go ahead, please.
All right, I think I've got to start on these state machines. Dr. Mitchell, are you around?
Is there something missing? The ACK on State Machine 2 never goes high. Has anyone else seen that?
Where are you talking about?
State Machine 2, the acknowledge signal.
What about it?
I don't see a state where it goes high.
Would you please go back to the PowerPoint? Go back to the PowerPoint, then back to this assignment.
No, Dr. Mitchell, are you back? I think I've got it. It might help if you do what is it, Mealy machine? I always get these backwards. If you do a Mealy machine, your outputs can change as the state changes.
I'm just saying in the instructions, it never says that the acknowledged signal goes high. Does anyone know why?
the input. That is differentiate between Mealy and Bohr.
Yeah, no, I get the difference. I just forget which names for which.
Yeah.
Um, honestly, I didn't read the instructions. I just looked at the timing diagram.
Would you please go through state 0 for the sending end on the left?
Absolutely. I'm gonna look at the timing diagram as I go through this to help. So starts in state 0. Once the input for enable goes to 1, we move on to state 1. State 1, we keep repeating as long as the request is high and acknowledges, that'll make acknowledge A low.
No, the request
I'm
is
sorry,
an output.
I was reading this backwards. Sorry, state 0, as long as it's state 0, it'll put enable high and move on to state 1 always.
So why didn't you put enable within state 0? S0?
I couldn't remember the proper way to draw it, so I thought it was this way.
No, drag a line before under S0 and put enable equal 1.
And then get rid of this.
So S0 enable will be equal to 1.
And then it'll move on.
S1,
State
S1,
1,
what will happen? It is gonna send the request.
yes. it'll
Another
send-
line, and I put request. Request equal 1.
But
And delete
the
it from here,
timing-
yes.
on the timing diagram, it stays request 1 output as long as acknowledge A input is 0. So would it not
Yes.
go out here where I have it, or does it go both?
It will remain on request. Oh, we lost it. Yes. The request will be sent out.
Okay,
Whenever you go to S1, I will send a request 1.
okay.
And I would remain as long as I don't have acknowledge it equal 1.
Yeah, okay,
Okay. When I have
So-
acknowledgement equal 1, I go to state 2. In
And
state
request goes to
2,
0.
I put request equal 0.
okay. I just drew this wrong. Yes.
S2.
Yep.
Request.
And then I can get rid of both of these. So it keeps repeating as long as acknowledges A equals 1 and moves back to 0 when acknowledge A equals 0.
Okay.
So then I gotta go.
I believe you can do the same thing with the second state machine.
Yeah, I'll go through it.
Okay.
I'll pop it back up once I'm done.
Okay. Take your time.
All right, I think we got this fixed. Okay, so redid state machine 2. Starts in state 0 and continues to loop until it gets a request B, which comes from state machine 1. If request B is equal to 1, it moves on to state 1, acknowledge goes to 1, and the enable register goes to 1. It doesn't matter what happens the next clock cycle, it'll move on to state 2. State 2 puts the enable register to 0 and continues to loop in state 2 as long as request B equals 1. And then if request B goes to 0, it moves back to state 0 and changes acknowledgement to 0.
I believe it looked correct. Thank you.
Thank you.
Would you please keep it for a while?
Oh, yeah, I could leave it up.
Yes. Put it
Sure.
back.
If anybody has
Will
questions.
you all please look at this one and let me know if you have something different? Take your time. We're going to
Isn't-
leave it for 5-10 minutes while you look at it and compare it against the timing diagram that's provided. Compare it against the timing diagram that is provided. If you have something different, please let us know. Thank you.
If you guys can't read anything, just ask. I know paint's not great.
Is there supposed to be a deassert counter on state machine 1?
What are you looking at?
State machine 1 shouldn't have a deassert on enable counter.
Let me take a look at the thing. This one page. Yeah, under this request, it should go enable equals 0. And state 1, because that would deassert it. Thank you. See if I can redraw this.
Yeah, because we have enabled for 1 clock cycle always. So
Yeah,
whenever it
and
finish with S0, it goes to S1, so it can set enable to 0. Yes.
Is it okay if we just submit this as like a table instead of with these circle things?
I believe the same will be for state machine 2 also. The enabled. Hello, Trevor? Trevor? Hello, Daniel? Daniel?
Hello, how's it
Uh,
go?
Does this state diagrams go well along with the timing chart that you have?
Yeah, I double checked it with the homework. At first, I was looking at the lecture and it wasn't looking right for the lecture, but then, yeah, I realized I was looking at the wrong document.
Okay. How are you gonna tackle this problem? How are you gonna, what will you be doing next?
I would probably work on the code for each state machine.
Yeah.
And then like probably the next thing would be just putting in the the skeleton, so the libraries and then the entities would just be like clock A and B and the RX data. And then, putting in all the internal signals. So like everything that's in the diagram. So like the counter and the enable counter, the request, the REQ. I would, so like just try to make like a skeleton.
What you are saying is 100% correct. What I will do is what you said. I am gonna start a new sketch for state machine 1, just the one to the left by itself. Looking at this one, what are the inputs and the outputs for this one?
For state machine 1, so it would be a clock A.
And you have the frequency of clock A.
Frequency?
Given. Yes, the frequency of the clock.
Oh, yeah.
It is given. And you can control that by the time delay. You have the process, clock, not clock, and there is a delay. Adjusting this delay will adjust the frequency.
Okay.
T is 1/f, correct?
Oh, I see, like what we did last time.
Yeah. So I have this clock as input. Do we have another input for state machine? According to diagram.
I mean,
we lost the diagram.
Enable.
The enable, no, get me. Would you, Kobe, would you get the
I hit the wrong
diagram
button.
back? Yes, Cody,
Sorry
please.
about that.
And the acknowledge.
The acknowledge is an input, yes, correct. And we have the output is what?
Enable and
request. Excellent. So I do a state machine with input as a clock, acknowledge, output, register, and enable. That's it. And check the timing diagram that you will get according to what you have. If it is correct, excellent. Put it aside. Start a new sketch for the state machine B, the second state machine. Again, you have here clock B, and you have inputs, that is request, and we have also the clock, and the output will be the second enable and the acknowledge. Again, you run it and you compare it against the timing diagram. If those two are correct, now you are ready to combine them. Of course, you will have acknowledge when you combine them together. The acknowledge will be a signal. The enable will be a signal, okay? Because those are internal. So the next thing is to go and start adding whatever you are missing and link the two state machines together. For example, acknowledge will be going from state machine B to A. Request will be going from state machine A to B, and so on. And of course, you will have the counter. The counter that is taking clock A and incrementing upon the enable. This is not an easy task, but whatever the diagram is in front of you, this is the brain of the whole thing. And as you said, it is in accordance with our timing diagram. So this is the base. We need just to go step by step and you will get it. Please start working on it, and we'll give some time on Saturday for this one. But if you go slowly, step by step, I'm sure you are gonna get the right answer. If you have any questions, we may discuss it on Saturday. Do you have any questions right now? Does anyone have any question right now?
I do have one question.
Okay, sir.
Do you think this would be easier to, I don't even know if it'd be possible to write it all in one file or to include files for each part and then put it together?
Whatever you like, whatever you like.
Okay.
When I said 2 files or 2 sketches, I meant to go with I can say the most tedious one, but it makes everything isolated. But if you want to make them in one file, no problem. As
Okay.
long as you have acknowledge as input, enable 1 as output, enable 2 as another output, request as input. You don't connect them with signals at the moment. When you are sure about each one, you can move to removing the input and output from the entity and start adding signals.
Okay, I'll sit down and see which one I think I like better. Thank you.
Take your time. As I said, this is a cornerstone in our whole course. This is a very important project, and it should have been a project by itself. But anyway, I didn't want to put a lot of grade on it because I know that it's not too difficult. And please look at the option. There is an optional part where it says, try to push it to the limit. Push it to the limit, that means pushing up the frequency. At certain frequencies, you are going to see it cannot respond that fast. Please include the state diagram with your submission. With your submission, I need to see the state diagram, the code, and the output waveforms. And please make a zip file of the whole sketch. The program itself, the whole sketch. Make it a zip file and include it.
I have a question.
The reason why I'm asking that, because I see some programs they don't look right, but the waveform is correct. So I want to, in some cases, I may try to run it myself. So I need the same sketch.
Professor, I got a question.
Yes, sir.
It says one of the inputs is reset, and then it says assert the reset for 100 nanoseconds at the beginning of the simulation.
Yes.
Does the reset,
Reset
it doesn't,
is the reset. Do you have a reset on the timing diagram you have?
it's not on the timing diagram.
Not on the
But it
timing diagram.
is-
So leave it as optional.
Okay. that's what I was
Don't
wondering,
bother
like, I
with
just-
reset right now.
Okay, sounds good.
Okay.
All right,
We need
Thank
the
you.
core. We need the core. How the state machines, the two state machines are speaking to each other. I want to see that the data of the counter is reflected on the output correctly. That
Okay.
is my main objective.
I have a question on how you want this turned in. So since you want it in a zip file,
Zip
Yeah.
file, the zip file, this is for the sketch itself. This is
with the
one file.
VHDL,
I need just two files. One file that will contain the state diagram, this is PDF file, one PDF file that is the state diagram, the code, the listing, code listing, and the output. This is one PDF file.
like we normally.
Number two is a zip file. This zip file is right click on the subfolder where you have the sketch, zip it. That's it.
Okay. Kobe,
Yes.
clear?
Yeah, that makes sense.
Okay, sir. If you have no questions, you may just leave. And if you have anything, I'll be available for you. Thank you all.
Thank you.
Thank you, sir.
Have a good evening.
Yes, sir.
You too.
Thank you.